I told you already that IP is quite simple. If something goes wrong, IP doesn't care. IP typically operates best effort. Yeah, we can define per hop behavior with differentiated services, but that's it. So if, for example, a packet dies in a router, so TTL is 0, tough luck. IP doesn't care. This is exactly where ICMP comes into play. I mentioned ICMP several times already in the context also of IP version 6 for address configuration, etc. So ICMP is quite important for controlling error management diagnosis. So what is the key idea? So ICMP is a layer 3 protocol, also a pretty old one, the Internet Control Message Protocol for IP version 4 already. And now assume use case 1, a router cannot forward a packet. IP itself doesn't care. But with the help of ICMP, the router can inform the source about this problem. The router doesn't have to. So you can configure a router, for example, that it will not send back ICMP messages. Because with the help of ICMP, you can also do some crazy things. So, but okay, in a normal situation, routers will send back an ICMP package if, for example, you cannot forward a packet. And this can be used then for diagnosis, for example, TTL is 0 or destination unreachable. So the ICMP message contains certain status information, certain control messages. So ICMP can be used by routers. And also ICMP can be used by hosts, for example, for the well-known ping. Ping uses ICMP request reply just to check if a host is online. You send a request and you get back a reply. So there's no TCP, UDP, whatever needed. It's just ICMP request reply. That's the idea. So ICMP can be used by routers as well as by hosts. Okay, how does ICMP look like? It's very simple. You have a certain message format, so a certain type. So what is the purpose of the message, a code, a checksum. There are more than 40 types defined. So we'll see some examples. Code, this additional information, rarely used, but the fields here, a checksum, same as for the IP header. So an example can be done. So error message, so to report an event, so you don't have to answer for this. And the error message includes the IP header that generated the error, so that we see, okay, for diagnosis, something went wrong. And an example could be the destination is unreachable. So that's the idea. There are also message category queries. This is to get some information from a node. And then you have a matching response. This was our ping. So the queries, for example, you ask the host ICMP request and you get a reply. So these are the queries. So you have the matching responses. For just if a router generates error messages, okay, then you just report about an event. You include the header, for example, then you can learn, okay, this was the IP packet, this destination, that's unreachable, then you can do something. Okay, so very simple format, 2 different categories, error messages and queries. ICMP transmit all these error and control messages on layer 3. So we already need IP packets, so we encapsulate ICMP in IP packets. And with the type, we can say, okay, what type of ICMP message it is. So our well-known ping uses type 3, that's officially called echo request, echo reply, or 11 is well known, so it's TTL equals 0, the packet is discarded and the router sends back an ICMP message. Then there are some more. Where do we use this? Well, for example, if you have a computer you host here and you want to see, or at least you believe, that this is the path of a packet, you want to see, okay, there are so many routers in the internet, and which is the path my packet takes. Then you have many routers, they're all connected, etc. And then you have a connection to the host, and you want to learn where the packet goes. Then we know a command called Traceroute. And although this looks like Traceroute down here to trace the network path, one way of doing the Traceroute is a quite brutal way. So what you can do is you send out packet with increasing TTL. So you start with, for example, TTL 1, and then this packet will die, in this example, in this router, and the router sends back an ICMP message. And this contains the IP address of the router, and you learn the first router. And then you continue with 2, 3, 4, 5, and you go up until you reach the destination. And you collect all the ICMP messages on the path to the host. And this then will tell you the routers this ICMP or this packet has taken. And then typically your data also flows along this path. But be aware that you cannot be absolutely sure, because in many routers ICMP is handled in software and packet forwarding is handled in purely hardware. Sometimes they even take different paths, etc. So this is just gives you a rough insight into the structure of the network. Then there are many components that simply do not answer. So if you run Traceroute, they will simply not answer to this, etc., etc. So that's one way of doing this Traceroute. So there are many types and options not used, not supported, and it depends on the intermediate systems if they support this. So there's also ICMP with version 6, IP version 6, but as we already learned, we use this for much more purposes, like this address configuration. Last subsection, neighbor discovery protocol, stateless automatic address configuration. Use this also for something we will learn, this automatic path discovery. Okay, so the point is IP version 6, there are no fragments anymore. So if we send a message that is too big, the router will simply send back packet too big. Okay, we don't fragment anymore. Why? The reason again was we want to offload as much as possible from the routers. The routers should forward and nothing but forward data. So that's one of the ideas, that then the routers simply send back, well, packet too big, and then you have to try with the smaller one until you don't get this packet too big message any longer. Then there are some other changes in the new version for multicast, etc., etc. So we can even support routing with ICMP. Okay, you can try all this on your own, well-known tools, and read all the details then in the RFC about ICMP with version 4 and version 6. Well-known tools, ping, well, you all know this, that we can ping certain hosts, and then we will get an answer from this. At least we think we get an answer from this site, and we get certain statistics and the well-known Traceroute, and this is to determine the used path for data. Yes, well, typically it goes this path, but there's no guarantee. And you see, some may not answer, some intermediate systems, plus there might be an arbitrary number of intermediate systems in between we do not simply see. This is only what we see, so only the routers that answer. And typically this is implemented by letting packets die in the router, and then they will send back a message, an ICMP message that your packet died. So then there are some combinations, Pathping, that's also quite interesting to learn a bit more about all the intermediate systems, so between your computer and in this case Google. So different tools on Windows and Linux, where you can find out the path looks similar to Traceroute, but you can also get certain statistics. So in this case, a bit boring, so it worked pretty well. But so it could be the case that you have certain losses, different delays, etc. So this gives you at least a very first insight into the network. So ICMP overall helps you a bit about controlling errors, diagnosis of the network. And for IP version 6, ICMP does a bit more, as we learned. Okay, so what else do we need? I already mentioned network address translation in the context of, well, IP address, scarce addresses, and also the transition from IP version 4 to IP version 6. And now I will explain how this works. Network address translation, needed, yes, hated, well, also hated. So why? Back to the motivation. We all need IP addresses, but IP addresses are a scarce resource. We run out of IP addresses. Version 4 don't have any IP version 4 addresses any longer. What can we do? Well, go to IP version 6, but we can also use NAT. Okay, and many providers like NAT, and some even think this is a good security measure, whatever. Oh, we will see. This is really a good idea. So network address translation, first of all, what is the idea? So, as it says, we translate layer 3 addresses. So we map an IP address onto another IP address. Okay? So what we can do is we can reserve a well-known block of IP addresses for a site local use. So within this site, we can say this is local. Here I can use whatever IP addresses I want. Well, really? Don't they have to be globally unique? So what happens if I send out a packet with an IP address that doesn't belong to the network but belongs to a computer somewhere here? Doesn't this cause problems? Yes. And this is exactly why we have NAT in between that translates the addresses. So we have addresses for site local use only. And this is a good idea where we can use private IP addresses. Okay? So one idea is using private IP addresses here. You could, in theory, use whatever you want. I mean, you basically translate address into address, but typically you use private IP addresses in your local networks. So quite common at home, if you have a DSL router, then you will have 192.168.0.1 for the router, etc., and dot whatever then for your devices. And the idea is everyone can do this. So you can have many of these local networks. So there's also a local one, that's local 2, that's local 1, and this computer maybe has 192.168.0.13, but there's also a computer here that has the identical address, 192.168.0.13. And this is not a problem because also this organization has a NAT here that then translates this address into a globally unique public IP address that's unique. And as long as you use two different addresses for the different machines, then there's no problem because no one will see these internal IP addresses. What is a side effect? If you have a packet that sneaks out somehow, no router will forward it because no one routes private IP addresses. And this is what some people say, oh, that's a security feature. We cannot send traffic directly to any of the local machines because they use private IP addresses. So we cannot, forward such packets in the internet. So no one can send a packet directly to one of the machines. And this is why many providers like this, because then they know, okay, no one can send anything to our customers. The customers can access everything, but no one can directly send something. There are many drawbacks, I will come back to this. But that's the basic idea. So typically we use the private addresses and all the other addresses are the public ones. And this creates scalability because we can reuse the same IP addresses with different sites. Okay, but if we communicate with computers on another site, we need a public address. So why is this still successful? Well, because quite often you don't have to communicate with the outside world. Many companies, typically communication happens inside their networks, and this communication will never and should never leave their site. So you can use your own address range, you can manage this on your own, and you don't have to ask for these addresses on your campus, for example. You can have the private IP addresses, and only those machines that have to communicate to the outside world, they need a public IP address. Additionally, you may control who's allowed to communicate with the outside world, and if you don't give this machine a public IP address, the machine cannot communicate with the outside world. Yet another feature. So the drawback, yeah, you need public addresses. So if all the machines permanently have to communicate with the outside world, then we don't have a real benefit, because then we need as many public addresses as we have private addresses, unless we do something in addition, a so-called port translation. I will come back to this. So in the end, network address translation, that's a technique to share the same public IP address among multiple computers. Why? Because if we do pure address translation, only the computer that really has to communicate with the outside world really needs a public address. If you do not communicate with the outside world, you don't need it. So only in the very moment you really talk to a machine in the outside world, then NAT has to assign you a public address. As long as you stay internally, you can live with your private address. So all the nodes need an IP address, and the IP address has to be unique in your intranet. Yes, sure. But you don't have to assign the public address. And most of the computers will stay local. They access local databases, etc. So you don't have to go to the outside world. So that's the idea of a NAT. So only if you go to the outside world, then you need this NAT. Then you need the device that then translates the private IP address and the public IP address and vice versa. So yes, we do break the end-to-end idea of, we will see, higher layer protocols. Yes, as we translate on layer 3 addresses. So we manipulate the header on the layer 3. Okay, so, but still many people see this as certain security argument, so then the local traffic stays local because we only use private addresses, etc. So yes, NAT provides this mechanism, we translate, and indeed it hides the internal network structure. We do not expose the hosts, because if we use private IP addresses, so it's private IP, we cannot even address them. But we break the end-to-end argument. And we'll come back to the end-to-end argument in many, many situations when we talk about certain security, authentication, etc. NAT doesn't help when it comes to denial of service attacks. So if you attack the NAT gateway, then that's it. And also what many people active in the network community think is that NAT quite often is an excuse for to deploy a real clean network architecture, because you can protect your machines even if you have public IP addresses. We know how firewalls work, etc., etc. So NAT, yes, NAT helped, because of the address shortage. But, so how does it work? Oh, the NAT, there's so many versions. There's the basic NAT, that's exactly only this, what I just showed you, netting, translating addresses. There is network and address port translation. Carrier create NAT that maps the already mapped addresses, etc., etc. NAT64 I briefly touched already during this issue of migration from IP version 4 to version 6. So how does it work? The very, very basic static NAT. So the idea is, let's hide the structure. Let's only show one public IP address per private IP address. We don't tell a private IP address. It doesn't make sense. So, and in a very simple case, we can even do a permanent mapping. Okay, but then we need really many addresses, as many as private ones. Okay, that's one way of doing it. So you see for the private IP address here, 192.68.03, that is this machine, we know, okay, NAT will translate this automatically to this public address. But then we don't have the big benefits. So typically it's a better way to do this temporary mapping. So we have a pool of public IP addresses and assign them on demand. So as soon as a machine here, as soon as this machine now wants to communicate with the outside world, then I say, okay, now let's say 192.168.03, we temporarily assign this public IP address to you. And this allows us to have way fewer public addresses most of the time. So that means we could have here thousands of computers with private addresses and maybe only, as shown here, 4 public or 400 or whatever, but way fewer, because only those machines that have to communicate with the outside world really need a public IP address. Okay, sure, I mean, during peak hours, if everyone wants to talk to the outside world, then we need as many public addresses as private ones. But typically, as I said, most of the computers stay local. So static is not a good idea. The static NAT, because we need as many external as we have internal, so that's not a good idea. So why not doing something else, a more dynamic way? So static NAT doesn't really save the number of public addresses. One-to-many NAT helps saving, because we always translate many local addresses to the same public address. Okay, but that's a problem. Sounds nice. So we use for all the internal machines the same public address. But what happens if now a packet arrives to this public address? Okay, so we need some more details for demultiplexing. Demultiplexing, that means, okay, they all use this IP address, but does this now belong to this computer or this computer? And typically, the more details are ports. So this is why we typically use NAPT, network address and port translation. And that's the most common technique. So we have one global, unique public IP address. That's what your DSL router has to the outside world. Only one for all your devices. But then this machine does not only translate your private IP into this single public IP, but also translates ports. And with the help of this combination, we can then demultiplex incoming traffic. Be aware, for all these NAT solutions, you can never directly communicate with the internal computer from the outside world. So it's not possible without any additional mechanisms to send packets from the outside to the inside world. But in normal situations, you at home, for example, or in company, you're the one activating the communication with the outside world. You access a server, you access email server, etc. And then you can communicate. So how does it work? Network address and port translation. So we have our company local area network here with all the different machines. And you have your router connecting to the outside world, and the router then may include the NAT, or you have the NAT box in your firewall. And if you have your packet, then you translate the internal IP address into the external one. But now we do a bit more. We not only translate here our IP address. So let's say if we have the local IP address, that's here. These are our private local IP address. We translate them into this global IP address. But as you see, we only use one. So we need an additional feature. And this is where we then use also a port mapping. So if necessary. So in this case, if the local port 1066 can be used also externally, you see, okay, there's a difference. If we have, let's say, the same ports, so doesn't matter, we can then use different ports to the outside world to differentiate the different destinations. And then we always have the destination, IP destination. Well, this depends on the application where you want to go. So we cannot play with this because this is where you want to go with your packet. So we cannot map anything here. This is the global address of whatever web server, telnet server, etc. So that's the idea. And if a packet comes in then from the external destination, we can then look up in the table, okay, for this destination, and then this computer with the address 1 or address 7 was the originator of a request, for example. So we can map both addresses and ports. So this all works pretty well with all the communication initiated from within the internet. So if you go from the internet to the outside world, then we create the entry in the table, and then we can come back and know where the packet should go, but not the other way around. So you cannot have, without additional mechanisms, an internal web server, for example. So you cannot give someone an access to your server in the internet. But that's one of the ideas for many people. So if you want to do so, you need a bit more. So for example, some more information that if there's an incoming request with port 80, then I automatically map this to the web server, for example. There's still some problems with some messaging protocols, etc. So in the end, for a clean architecture, only really more public addresses really solve the problem. Because if we have all this address translation always in between, we have problems. So one way of fixing the problems, well, the clean way is having more addresses. But one way of solving the problem right now is that immediately after being turned on, your devices connect to a well-known server, and then everything runs via this connection. That's what also mobile phones do. They directly connect Apple, Google, and then they run many things over this connection. But it has to be initiated by the client. So you cannot directly access the client. There are more NAT versions or NAT deployments, carrier grade NAT, also known as large scale NAT. So that's basically a NAT box for many customers, so for a whole street, a suburb, etc. So that you have a NAT box at home, but then your carrier then says, okay, I will then again map all this then to another address. Breaks the end-to-end principle, quite difficult sometimes for well-known ports, etc. Then I already talked a bit about NAT64. That's how to connect IPv6 hosts to IPv4 servers. So we can also map here. So you can take a look in this subsection. So NAT changes here the IP headers and maps version 6 to version 4. So this is not a tunnel, but really mapping of addresses. So in principle, you can map whatever you want onto whatever else you may think of. So, and here it's version 6 to version 4 addresses. So there are many issues. If you think of checksums, so you cannot simply change IP addresses without changing the checksum. Then there's also a problem with fragmentation, encryption, some other issues. So you have to recalculate checksums because you cannot simply change port numbers, because in IP, the strange thing is that the port numbers also go into the checksumming. So if you change something, you have to change the checksum. Also fragmentation. So if you deliver things out of order, you need additional states for the fragments in the NAT box. You see, it's getting a bit more complicated. What happens if you use encryption? So if something is encrypted, you cannot change anything. So assume you use IP security and you fully encrypt already, you don't see the ports. Well, you have to see the IP addresses. Yes, you can map something there, but maybe not the ports. You cannot perform any changes there. And then there are some higher layer issues. For example, there are some protocols on the higher layers that may include IP addresses for whatever, for authentication, for this and for that. Now we have a problem. So we may have problems on higher layers, and then also Traceroute. So if you have TTL issues, ICMP includes IP headers of the original datagram. Do you translate this or not? How do you handle this? So diagnosis has a problem. So also DNS. What happens with DNS? So if you change your address to the outside world, no one will find you. This is why we have dynamic DNS and things, and there are some NAT boxes that try to tackle these issues, and then you change upper layer data and things that... So, what do we think about NAT? There is, at least we have to say, a controversy about NATs. Yes, we all have to agree, NAT saved the internet by allowing it to scale. Because IP version 6 was not there. It was invented, was standardized, mid-90s, but not available everywhere. So massive reuse of private addresses really helped a lot. So we could do more with less public addresses. But on the other hand, and that really is a problem, NAT kills a fundamental principle of the internet. This is the end-to-end communication. And this now can only be initiated from one side. So if we are a bit more strict in the definition of the internet, you're not on the internet with your machines at home. They do not really participate. So this is kind of a half duplex thing, whatever. It's only unidirectional from the beginning. So it's there is hope that really the IP version 6 adoption will in the end eliminate the need for NAT. And we have real end-to-end communication, and you can really connect all the things back at home from anywhere without any headaches. So if we really have IP version 6 and clean network structures and the security mechanisms, we don't need NAT anymore. And this would help a lot when it comes to looking into the network diagnosis, traffic management, etc. Okay, so going back, ICMP. What about IP? Does IP care if something goes wrong during packet transmission? So why do we need ICMP? What is the role? Compare IP version 4, IP version 6. Then I talked about NAT. NAT is used almost everywhere. Why? What was the initial reason? What are the drawbacks? What are the advantages? What about NAT and security? And what about clean architecture using IP version 6? Do we then still need NAT? Why?